My name is Ziye Yang. I'm a software engineer at Intel. It is my great honor to present my topic in persistent memory computational storage event. And my topic is accelerating operations on persistent memory device with hardware-based memory offloading technique. Here is the agenda. Firstly, we will introduce the background and the problem. The problem is that the relative high CPU overhead when you use CPU to drive operations on persistent memory. Secondly, we will present our proposed solution. We will use hardware-based memory offloading technique to offload the CPU tasks when doing operations on persistent memory. Then we will give two use cases. The first use cases, we will describe how to enable hardware-based memory offloading technique in storage performance development kit. Then we will introduce how to enable hardware-based memory offloading technique in Ceph. Finally, we will have a conclusion. Here comes the background and the program. With more and more deployment of non-volatile memory devices in data center, for example, if we deploy Intel's Optane persistent memory, then the CPU resource on the host becomes a bottleneck while operating on persistent memory devices with application director mode under high workloads, instead of using traditional hard disks or SSDs. In the right part, we give a diagram to compare the difference why CPU drives operations on traditional SSDs or persistent memory. In the left diagram, the host CPU says, I'm fine to serve 20 virtual machines. My brother's SSDs will have DMA capability and can help me complete IOs. But if equipped with persistent memory, the host CPU says, I can only serve 15 virtual machines because I'm very busy, since there is no DMA capability available from persistent memory. So the root cause of this situation is clear. Data operations between persistent memory or memory is different from data operations between memory and device. For the later case, there is DMA capability or RDMA capability on such device, and the CPU will not be the bottleneck. So how to offload the work from CPU with offloading techniques while operating on persistent memory is a valid requirement. For example, cloud providers would like to utilize the important CPU resources in customer visible workloads. They can virtualize CPU resources and sell the virtual CPU resources to customers. For example, they can be used to launch customers' virtual machines. If we can save the CPU cycles on persistent memory, it will definitely generate benefits. So here comes our proposed solution. Our solution is that we will leverage some memory offloading devices, such as Intel's IOAT technique or data streaming accelerator technique or other vendors' techniques to address this issue. And those memory offloading devices should support offloading the following operations on persistent memory. For example, the memory movement between DRAM and the persistent memory. And if we select those devices, there should be a user-friendly software in both kernel or user space to support the offloading requirements. And how to efficiently leverage those memory offloading devices? We know there are two methods to integrate memory offloading devices. It is the sync and the sync method. And if we use the sync method, the integration overhead is low. The users do not need to change the code very much, and the advantage will not be clear in CPU resource utilization and the performance improvement for the workloads while utilizing the hardware-based memory offloading devices is not clear. So we need to use a sync method if the workloads we want to interrogate uses async threading mode. But really, the integration overhead will be high. But if we can do this, there will be definitely CPU resource saving, and there will be performance improvement for the workloads because the hardware memory offloading devices can collaborate with the CPUs to complete their tasks on persistent memory efficiently. And to demonstrate our idea in this presentation is practical, we present two examples. One example is integrating IOT or DSA in storage performance development kit. And we will accelerate those storage applications which utilize SPDK framework. Then we will present the second example. It is integrating data mover library to drive DSA and accelerate persistent memory operations in Ceph. Here comes the first use case, memory offloading technique, enabling in SPDK. So what is SPDK? SPDK is a user space based storage performance development kit. It targets to improve the performance of storage applications which utilize high-speed storage devices such as mini devices or others. We can see in SPDK library, it can be divided into 3 layers. The lowest layer is the drivers layer. SPDK provides a user space mini driver to utilize the PCIe SSDs. And in the middle layer, there is a block device abstraction layer. It can support different block device based on different device types or implementations, and it is similar to kernel's block device implementation. And in the upper layer, SPDK provides several reference implementations of high performance storage application demo, such as SPDK iSCSI target or SPDK's MNE fabrics target POC or reference solution, which utilize all the SPDK libraries, such as the block layer or the lowest MNE driver. And inside the SPDK, there is a acceleration framework. We name it as Excel framework. It can utilize different memory offloading device technique, such as Intel's DSA or IOT. And it can also integrate other vendors' hardware-based memory offloading devices into this framework. If we obey SPDK's acceleration framework SPDK acceleration frameworks API. If we use SPDK's acceleration framework API, we can use SPDK Excel rated functions instead of the lower layer functions defined in DSA low-level library or IOT low-level library. For example, we will not use SPDK IDXD submit field rated functions. And ideally, if there are no memory offloading devices, we can directly use the software module. It means that we can use CPUs to drive the memory or persistent memory based operations. So how to offload operations on persistent memory? In SPDK, we design and implement a new bdev named as Pmem based on persistent memory and SPDK's acceleration framework to demonstrate that hardware-based memory offloading engine can help improve the performance. And our purpose is to leverage IOT or DSA enabled in SPDK Excel framework to reduce the CPU participation overhead. Ideally, such offloading technique should be provided by persistent memory development kit. But currently, PMDK library has some limitations. For example, it only provides the synchronized API interface. So it is not quite efficient to utilize DSA-based memory offloading technique. But we know that there will be an ongoing work inside PMDK recently. And the PMDK does not have the ability to plug in memory offloading engines. So this diagram shows the high-level design of Pmem Excel bdev based on SPDK Excel framework. In this diagram, we can see there is a new block implementation which marked with purple color compared with the previous implementation. Pmem bdev, it just uses the CPU and utilize Pmem block library inside the PMDK. We can see that Pmem Excel bdev will be more efficient than the previous solution. So if we summarize that, currently we choose use DX mode directly. We want to continue discussing with customers whether DX mode can fully satisfy a customer's requirements. And we provide the ongoing patch in public to describe our current progress. And in this usage, file system cannot be viewed directly on the character device. The persistent memory devices can be partitioned into different character devices. And SPDK process can directly use one or several DX-like devices directly, and those operations on such bdev based on persistent memory can be offloaded through DSA in SPDK acceleration framework. And with this implementation or the collaboration by CPU and the DSA, there will be performance improvement. But due to Intel's Ceph platform is not released yet, we will not show the performance comparison in this presentation. And here comes the second use case, memory offloading technique enabling in Ceph. In Ceph, there are several stores such as File Store, Bluestore, or C-Store. Here, we will introduce our work in Bluestore and also oversees the potential work to leverage DSA in Ceph C-store. So the first one, we will use DSA to offload persistent memory operations in Bluestore. And we propose the following approach. We will leverage DML data mover library or IDXD config library to invoke DSA capabilities to offload the operations between memory and persistent memory. Step 1, we can use the synchronized API in DML to offload the CPU operations. And the expectation is that the functionality can work. It means that we can use the synchronized API in DML to offload the data movement between memory and persistent memory through DSA. And we provide the following two patches. And currently, the two patches are merged in Ceph's master. And the second step, we will try to utilize the synchronized API in DML to fully offload the CPU operations. And the expectation is that there will be some performance improvement and mitigate the CPU pressure while operating on the persistent memory in Ceph's Bluestore. But due to current Ceph architecture, this work is not easy. Different with applications which use SPDK's synchronized programming framework, it is much harder to leverage synchronized APIs to drive DSA in Ceph. So in phase 2, we will try to offload persistent memory operations in C-store. Because C-store uses C* framework, it is also a async programming framework. So we can expect the good async behavior in C-store. So when we integrate DSA, we will do the following works. For example, we will use DSA to offload some memory operations inside the C-store. For example, we can offload copy or CRC calculations between memories. And then we can also use DSA to continue optimizing operations on persistent memory in C-store with async behavior. Since we just described that C-store uses async programming framework, so we believe that it will generate huge benefits while using DML through a data mover library's async interface. Here comes our conclusion. In this presentation, we realize the overhead or bottleneck of CPU to conduct data operations between persistent memory while performing storage workloads. Because data operations between memory or persistent memory is different from data operations between memory and device. For the later case, there is DMA or RDMA capability from those devices, so CPU will not be quite busy. But if we directly use CPU to rewrite on persistent memory, the CPU's overhead is relatively high. So we need some hardware-based memory offloading devices, such as Intel's IOT or DSA engine to offload the work by CPU. So in this presentation, we introduce our solutions based on those hardware-based memory offloading engines. We introduce two usage cases to offload persistent memory through those hardware-based memory offloading engines. For example, we leverage SPDK acceleration framework to offload operations on persistent memory, and we implement new persistent memory-based bdev in SPDK, which utilize the underlying hardware-based memory offloading devices. And we can see some performance improvement. And we also introduce our work on how to use data move library to drive DSA on persistent memory in Ceph's C store. So what's our next step? We will continue improving the performance on persistent memory through memory offloading engine based on DSA or other vendors' hardware-based memory offloading technique. For performance report, we will try to publish it later after Intel Ceph Rapids platform is launched. So it is all my presentation today. Thanks for your viewing and listening to my presentation. That's all. Thank you.